Hello, so let us look at few more identities in today's session. So the first problem is show that for all integers n greater than or equal to 1, summation r equal to 0 to n minus 1 whole raised to r, ncr is equal to nc0 minus nc1 plus nc2 minus etc. plus minus 1 whole raised to n NCN. And the second identity is NC0 plus NC2 plus etc. NC2K plus etc. is equal to NC1 plus NC3 plus etc. NC2K plus 1 plus etc. is equal to 2 raised to n minus 1. So let us look at the proof of this identities. So we have x plus y whole raised to n is equal to summation r equal to 0 to n ncr x raised to n minus r y raised to r varum. So this is a binomial expansion. Now for obtaining this, so put x equal to 1 and y equal to minus 1. So on the left side you will get 1 minus 1 whole raised to n, that will be equal to summation r equal to 0 to n ncr. So this is 1 raised to n minus r minus 1 raised to r. So the left side becomes 0. So therefore we will get, so here you have equal to 0. So therefore we will get summation r equal to 0 to n ncr minus 1 whole raised to r is equal to 0. So upon expanding the terms, you will get nc0 minus nc1 plus nc2 plus etc. So the last term will be minus 1 whole raised to n ncn is equal to 0. So that is the proof for the first part. For the second part, we need to show that nc0 plus nc2 plus etc. അതായത് even വരുന്ന r even ആയിട്ടുള്ള combinations, so that is equal to the sum of combinations where r is equal to odd. So that is obtained directly from this equation. First part in നമുക്ക് കിട്ടും. So nc0 minus nc1 plus nc2 minus nc3 plus etc. plus minus 1 whole raised to n ncn is equal to 0. So that implies nc0 plus nc2 plus etc. nc2k plus etc. that will be equal to nc1 nc3 plus etc. nc2k plus 1 plus etc. And now we need to show that this sum is equal to 2 raised to n minus 1. And now we have summation r equal to 0 to n ncr. So this is equal to 2 raised to n. So this we have seen in the last class. The nc0 plus okay. So that means nc0 plus nc1 plus nc2 plus etc. ncn will be equal to 2 raised to n. Now we know that nc0 plus nc2 plus etc. is equal to nc1 plus nc3 plus etc. So therefore this can be written as 2 times nc0. ഇത് രണ്ടും equal ആയതുകൊണ്ട് 2 times nc0 nc2 plus etc. nc2k. So plus etc. This will be equal to 2 raised to n. So that implies nc0 plus nc2 plus etc. nc2k will be equal to 2 raised to n minus 1. So which is the already equal to nc1 plus nc3 plus etc. nc2k plus 1 so that gives the required result. So these are the two identities. Now let us look at the next identity. So the next identity is show that for all integers n belongs to n, summation r equal to 1 to n, r NCR is equal to n 2 raised to n minus 1. So for this, let us start with x plus y whole raised to n, that will be summation r equal to 0 to n NCR x raised to n minus r y raised to r. Now put x equal to 1 in this expansion. So that will give 1 plus y whole raised to n equal to summation r equal to 0 to n NCR y raised to r varum. And now what we do is you differentiate with respect to y on both sides. So that is going to give n 1 plus y whole raised to n minus 1. That will be equal to summation. So when you differentiate here, it will start from 1 to n. So NCR r y raised to r minus 1. Now again for getting the result, so put y equal to 1 in this. So that implies summation r equal to 1 to n r NCR will be equal to so you will get n 2 raised to n minus 1. So that is the required result. Now the next identity is called as Vandermonde's identity. So let us look at what is the identity, and we will see an algebraic proof and combinatorial proof for showing the identity. So show that for all m n r belongs to n, summation I equal to 0 to r MCI n r minus I is equal to MC0 NCR plus MC1 NCR minus 1 plus etc. MCR NC0. So we need to show that this is equal to m plus n CR. So this is called the Vandermonde's identity. And first let us look at an algebraic proof for this identity. So let us look at the first proof. Now consider, so 1 plus x whole raised to m plus n equal to, so this is equal to 1 plus x whole raised to m into 1 plus x whole raised to n. Now let us expand this function as series both on the left and right side. So expanding these functions as series, we get, so the first one is summation I. So let us take k equal to 0 to m plus n c k varum. Then you will have 1 raised to k x raised to 1 raised to m plus n minus k. അപ്പോൾ അത് 1 തന്നെ ആയിരിക്കും and x raised to k വരും. Okay. So that is the expansion you are getting on the left side, and on the right side, so let us take I equal to 0 to m. So you are going to get mc I x raised to I varum into summation j equal to 0 to n nc j varum ncj x raised to j. Now let us take the product on the right side. Okay, so on the right side, ആദ്യം constant coefficient ഉണ്ട്, then you have coefficient of x square up to coefficient of m plus n. So let us look at what is the coefficient of each. അപ്പോൾ x raised to 0 വരുമ്പം first term mc 0 വരും, second term nc 0 വരും. So the only constant you obtain when you multiply both will be mc 0 into nc 0. Now let us look at what is the coefficient of x. അപ്പോൾ coefficient of x കിട്ടണമെങ്കിൽ ഇവിടെ constant എടുക്കുക, ഇവിടെ x ന്റെ coefficient എടുക്കുക. അപ്പോൾ you will get mc0 nc1, then ഇവിടെ x ന്റെ എടുക്കാം, ഇവിടെ constant എടുക്കാം. So that will be mc1 nc0 into x, then x square ന്റെ coefficient എന്ന് പറയുന്നത്, so mc ഇവിടെ constant, ഇവിടെ x square, so mc0 nc2, then രണ്ടിടത്തും x ന്റെ coefficient, അപ്പോൾ mc1 into nc1 plus ഇവിടെ x square ന്റെ coefficient, ഇവിടെ constant, so mc2 nc0. So that is going to be the coefficient of x square. So and the last x raised to m plus n ന്റെ coefficient എന്ന് പറയുന്നത് mcm into ncn x raised to m plus n. And now let us compare the coefficient of x raised to r on both sides. So now comparing the coefficients of x power r on both sides. So that implies, so on the left side the coefficient of x power r is m plus n c r. So m plus n c r. On the right side you will have mc0 ncr varum, then mc1 varumbam ncr minus 1 plus mc2 then r minus 2 plus etc. The last term will be mcr nc0. So this is the required entity. So that implies m plus n cr will be equal to summation I equal to 0 to r mci ncr minus I. So this is the proof for the Vandermonde's identity. And now let us look at the second proof. So the second proof is a combinatorial proof.